end the class with the definition of entropy. You guys are mostly all here yesterday, right? As I understood from talking to you in the past 3 days, of course, this thing you have to like study it for like months to get it right. But there is all this confusion about quasi-static and reversibility, and how to make problems out of it. I don't know. I don't have an answer for that. I've done the best I can to different, to tell you what quasi-static mean and reversible mean. But the whole idea is that eventually you don't have to worry about all that anymore, right? People do chemistry without worrying about reversible process and irreversible process. You do to some extent, but after a while, it's in the back of your mind, and all you need to do is calculate the free energy and entropy, right? And so that's the purpose of this class, right? And we'll go a roundabout way, but eventually we'll get there. We will talk about heat engine, reversible engine, and this second law of thermodynamics. The point is not to calculate, as I said yesterday, the point is not to calculate the efficiency of an engine, right? Because that's not the purpose of the class. This is, I don't know how to actually do that for a real engine, and I have no interest in refrigerator either, right? But I use one. But the main thing is to actually try to describe a physical process thermodynamically, right? And to achieve that, you need to define the concept of entropy, and that's what we want to do here. So let's start by, we're doing it roundabout way, but this is the statement of the empirical statement of second law statement. One is by Clausius, basically. I did this yesterday on Monday. No process is sole effect, and this is the important condition here, is that heat flows from reservoir at low temperature to a reservoir at high temperature, right? So this process is not allowed. So if I have two reservoir, TL and pH, I cannot just transfer heat like that. It doesn't work, right? It's not reversible. The other process is allowed, right? Transferring heat from high temperature to low temperature is okay, right? But you cannot go backward, right? And the other statement is by Kelvin, although it's actually probably by Carnot before. No thermal process, the sole effect is to extract heat from a system and convert it all to work, right? You cannot just take heat from a bath and then convert everything to work. The reverse is okay. The reverse you can do, right? You can just take work and convert it all to heat, right? This is just, rubbing your hands shows that, right? The Joule experiment discussing the book shows that, right? That's how he acted the first experiment to show that heat is actually a mechanical energy, right? But the reverse will not happen. Otherwise, we'll solve our energy problem, right? This is the ocean. It has a lot of energy in there, right? At some temperature T, right? And if you can make an engine like that, then we're all rich, right? There is no more problem. Energy is solved because then you can just do whatever you want. But this doesn't happen, right? And that's the purpose we want to. And that's what we want to understand, right? The concept of entropy. Especially these days, because we talk a lot about conservation of energy, but you guys know, right? Energy is always conserved, right? First law is always true, right? So what are they talking about when they're talking about conservation of energy? If you say, well, we need to conserve energy, I said, well, energy is always conserved, right?
Conservation of usable energy, like mechanical energy.
That's a good point. Yes, conservation of usable energy, or sometimes the more appropriate term is free energy, right? From chemistry, we talk about free energy, induced free energy. That's what you want to conserve. It's mostly about making sure that entropy is always low, right? Having a good source of low entropy. is the whole, I mean, motor size. So let's see if we can formulate that. And to do that, the first person who actually did it was Carnot. He had this insight. This is basically his insight, right? Or his or people during that time. Processes like this will not happen, right? If you can have processes like this, then you have perpetual motion. Right? You can design perpetual motion. The fact that you cannot, that was people at that time, and then he basically used that statement to try to construct things that we will do. We talk about heat engine. Where was I? So what Carnot did was to construct reversible heat engine. Okay, that's operating between TH and TL. Right, two reservoirs and connected by an engine, right? That you extract heat out, right? And it turns out the easiest way to do this is by two processes that we already discussed on last week on Friday, which is constructing the engine out of isothermal and then adiabatic process. Okay, so you can think of your engine as a piston. Right? So what you do is you make a thermal contact with your piston with the two reservoirs, TH and TL. Right? You do the expansion. The first part of the process is going from A to B, right? At TH when you're in thermal contact with TH, right? And it leads to this expansion. It's an isothermal expansion, right? And then what you do is you decouple the piston from the thermal contact, right? And then insulate it and let it expand even further, right? And then you go from B to C adiabatically. Then this is adiabatic. Okay, this is isothermal. Okay. And you do this at the expense of the internal energy of the system, right? Temperature drops. So the temperature of the piston drops until it reaches TL, then you stop, right? And then you bring your piston in thermal contact with the heat bath of low temperature, TL, and then let it contract. Okay? Until it reaches a point D, the appropriate point D, in such a way that you can connect it back adiabatically to A, right? You decouple it from the EPL, right? And you let it contract even further. When it contracts, you increase the internal energy of the piston, right? The system, right? Temperature rises all the way back to TH, right? And then you're back to square one.
How do you increase the thermal energy immediately?
How do you?
Yeah, how do you increase the thermal energy?
Oh, by the adiabatic contraction,
yeah.
right? Because you're pushing against the piston, right? And heat cannot escape, right? The whole thing is insulated adiabatically, right? So what they do against the piston is used to increase the thermal energy, the internal energy of the system, right? So temperature rises all the way back to A, right? Okay. So I don't want to show it again, but from this consideration of Carnot Engine, we actually did a long calculation on Monday, but we did show that the efficiency Carnot efficiency is given by 1 minus TL over TH, right? Right, because the efficiency is actually defined as work divided by QH in this case. Right? It's the amount of work that you can do per unit heat that you extract from the high energy reservoir. Right? And this is just equal to 1 minus QL over QH. So this is the efficiency. Let's see. The point, of course, as I said earlier, is not to actually calculate efficiency. The main thing, that the lesson that you want to get from this is that for Carnot cycle, okay, QL over QH is just TL over TH, right? Okay, and if I rewrite this equation, right, I can rewrite it, just rearranging the variable, and I get QH over TH is equal to QL over TL, right? I'm doing things completely out of order from my notes, so I got confused. Okay. But we know from that process, right, the QH is actually positive, right? Because energy goes into the system. It transfer. That's right. Remember, U is equal to, this is first law, right? Q minus dW, right? The internal energy is of the system increases if you transfer heat into it, minus the work done by the system, right? So if QH is positive because it raises the internal energy of the system, and then QL is actually negative, right? Because heat at this point leave the system. Okay? So for Carnot cycle, just draw it something like that, right? QH over TH plus, should I do it in more carefully, is equal to minus QL over TL, right? I remove the absolute value sign here, okay? And then I just put everything on the same side, QH over TH plus QL over TL is equal to 0, right? This is equivalent to that efficiency of the Carnot cycle, this one. Right? This statement is the same. Right? Now, the next thing I want to do, that's all nice and fine. The next thing I want to do is to prove to you that all reversible engine operating under H and TL have the same efficiency as Carnot. Okay. And then all the reversibles engine is less than E Carnot. Okay, this is proved under Carnot actually. So how do you do that? The proof is actually simple. Maybe I'll assign this as homework, not this one. The statement of this equivalency proof is going to be very similar to the one I'm doing. Maybe I'll do that as a homework. So let's prove the second statement first. This is A. Let's prove B first, right? Now, we prove it by contradiction, right? Suppose I have an engine, right? I have an engine E, and the efficiency of E is greater than E Carnot. Then, if that's the case, then say I have something like this, pH, PL, right? If it's an engine E, right? Suppose I extract Q1 out of pH, right? So Q1 leave pH, and then I give the work W prime, right? And then you dump Q1 minus W prime into the lower reservoir. Okay? See? So now the efficiency of this engine given by W prime over Q1, right? Now suppose this is actually greater than E Carnot, right? Then I can, and Carnot engine is a reversible engine, right? This is a reversible engine. Then I can insert a Carnot engine here, right? And have it act as a refrigerator, like that, because it's reversible. Right? Carnot is reversible. So this is TL, right? So I suppose I can extract Q1 here, right? And dump it up there, right? Sorry, Q1. And suppose I in such a way, so this is a reversible Carnot. In such a way that you actually dump Q1 back into the high temperature reservoir. Okay? And the efficiency of this engine is W over Q1, right? Okay. Now since W prime has to be divided from this, right? W prime is equal to greater than W, right? Then what I can do is I can take a little bit of, I can take the W portion of the work that this engine does, right? And insert it into, insert W here, right? Okay. And then let it work W minus W1 minus W. Sorry, maybe it's confusing. Is that right? Is this confusing?
Yeah, you're double using W.
Okay, so there's engine E, right? Engine E is any engine, irreversible engine, right? Okay, it can extract Q1 out of pH and do work W1, right? And since the efficiency, if we assume that the efficiency of this engine is more efficient than Carnot, right? Then W prime is greater than W, right?
Is W from the Carnot engine?
W is on the Carnot engine.
Going into it or out of it?
Going into it. I'm operating it in reverse. I'm
Oh, I see.
operating the Carnot engine in reverse. Because it's reversible. Carnot engine is reversible.
So work's being done on,
Say it again.
is being done on a system?
Yeah. I guess I should probably be talking about in two steps. I should talk about the refrigerator first. Maybe. The point is that Carnot engine is reversible, so I can operate it backward. Right? Where is my phase diag? Where is my PV diag? Right? Right now you should be comfortable with this problem. Right? A, B, C, D. I operate like that, it acts as an engine. Right? You can get it worked out. But I can also operate it backward, right? I can operate it like this. Laterally. Right? Then it acts as a refrigerator. You can see this in the okay, operating in reverse. Reverse. So what you do is this. Engage. Down. Engage. I'm just reversing all the F.
Why does in this one the W come from the E?
Oh, I'm just trying. I'm trying to show by contradiction. You will see, right? But what I want to do is since this W prime is greater than W, I will take the W portion of it and have it to work on the Carnot engine, right? So the W goes this way, right? And then the heat, the work that you extract is only W prime minus W. Sorry, I'm not going this whole discussion, but you get the idea, right? Okay? So, and this is doable because you assume that the efficiency of the engine is larger than the Carnot efficiency. Okay? So, look at this diagram. Then what you have is, if you look at the upper reservoir, right? This is TH. Right? You have Q1 coming this way and Q1 coming that way, right? They cancel. Correct? So I have this engine, I have my engine, and then the engine of interest, and then this is TL, right? So here I have Q1 minus W prime, and here I have Q1 minus W, right? And then W goes this way, right? And then here I have W prime minus W, okay?
It's minus W?
Yeah, because I take
Not on the
I
left
take the
side?
W portion of it
On the
and use it to pump.
I mean the
The Carnot
going,
engine.
on the left side, the bottom arrow going up.
Yeah, it's going up because it's operating backward. The Carnot engine is operating in reverse.
Oh, that's the heat, right? So the
Yes,
same
yes.
heat is going
Yeah,
down
this is the
and,
heat.
okay,
This is the heat actually going backward.
yeah.
Okay, so then what you have here, right? This is heat being jumped into TL. This is heat being extracted from TL. What you get here then becomes, if you do the math right, this becomes W prime minus W, right? I'm just looking at the absolute value. I'm always very better with my negative sign. Okay? So what you have is that heat, this amount of heat being extracted from TL and being used to convert it all to what? Right?
Why is the heat for the irreversible engine going into TL not Q1 minus W prime minus W?
Oh, because question, right? I have Q1 coming in this way, right? right? And then I have W prime going out from the engine E, right? I take the W portion of it and I use it to pump the Carnot refrigerator, right? So the free work that you can do to the outside world is given by W prime minus W, right? And the heat being done in the TL is just Q1 minus W prime. That comes from the efficiency, right? Q1 W prime, Q1 minus W prime. Okay? So what I have here then, what do I have here? This is a violation of Kelvin, right? Because what I have is I extract heat from TL, this much heat from TL, and convert it all to work. Right? Of Kelvin. Is that right? Okay. Therefore, this statement E, so I'm proving it by contradiction, this statement E, the engine greater than the Carnot, okay, is false. Right? The best you can do is E of the engine has to be less or equal to each other. Oh, because what happened from this, I think it's confusing because I did some of my sign wrong perhaps, I don't know. But if I look at this diagram here, right, Q1, I can consider this whole thing as one engine. Right? This whole thing is one engine. This engine here is a combination of Carnot engine and the engine E. Right? What happened is the Q1 cancel, right? So then the upper reservoir, you can disregard the upper reservoir, right? So to the left, just with the lower reservoir and then this dual engine.
Why doesn't the lower reservoirs Q cancel also?
No, they don't, because this is Q1 minus W prime.
Oh, and now
This is
it's
Q1 minus W.
Oh.
Right? So they don't exactly cancel. The difference is W prime minus W.
Oh, it's because that W goes into that, whereas the
Yes.
W prime minus W goes out.
This is clear?
So the contradiction is that you're just getting energy.
So yeah, I'm just basically extracting the heat from TL, from the ocean, right? And converting it all to work. Right?
Oh,
This
so
is,
that
because you're not dumping it.
yeah, I'm not dumping anything anyway. Right? So it's a violation of the Kelvin statement. Right? I mean, this will solve your energy problem. Yes.
I'm a little confused by like in the Kelvin statement what it means by solar effects. Does that mean without external work?
Meaning that there is no other effect, right? Things will. So after all said and done, everything goes back to the engine goes back to the original starting point.
So here, if you ran it, then you would
Yes,
just get
yes,
work. and
right.
everything
So
else would-
correct. This is an engine. An engine, by definition, is a thermodynamic process that goes back to its original beginning of the cycle. Right? So yeah, after you do one cycle of this, right? What you have is you extract it from TL and dumping it all to work.
Okay.
Right?
What is it about the Carnot cycle that allows us to say it's reversible engine process, and what are other processes that are reversible?
It's reversible because we talked about this before. You could struck a Carnot cycle out of isothermal process and adiabatic process. So they're all reversible. Right? We discussed this. So basically, this process here, this whole process, if it's done slowly enough, is reversible.
So why only those two processes?
That's just the one that we use for defining a Carnot cycle. But you'll see that in the end it doesn't really matter, right? So I'm only halfway there, right? Because I'm proving statement B, right? That efficiency has to be less than Carnot, right? But I can use the same argument right? Exact same argument to prove that all reversible engines have the same efficiency. As Carnot. So this is the Carnot engine, it's the same Carnot engine, right? Okay. And this is a reversible engine 1 say, or a reversible engine, right? Operating under the two temperature heat path, H and TL, right? So this Carnot operates in reverse, right? Okay, and then by the proof of B, we show that ER has to be less or equal to C, right? Okay, this is quite clear. But I can do that. I can flip because this is reversible. This R is reversible, right? I can flip the two. And operating R in reverse. Right? And with what I have is EC, is that right? Yeah, EC has to be less or equal to R. Okay. And then by these two statements, I get EC or R equal to EC and equal to any reversible engine. Okay. All reversible engine operating under 2 back will have the same efficiency.
What's another example of a reversible cycle?
Sorry?
What's another example of a reversible cycle?
Operating under two temperature, TH and TL. I think the answer is just Carnot. But it's a general, I'm generalizing, right? So you don't have to be specific in this proof. Okay. Is this clear so far? Okay. Okay. So, and there's a point to all of this. We're working. So we prove that. This is always the case. But sometimes summarize E reversible is equal to E Carnot. E reversible is less than E Carnot. So with that, any engine will have this kind of thing. Okay. Now, efficiency is defined as 1 minus QL over QH, right? Okay. Operating under the reservoir, right? And this has to be less or equal to 1 minus TL over TH. Okay? Okay. So let's be see over here, right? So the one cancel, right? Minus QL over QH is to be less or equal to minus QH, right? Okay? I'm always confused about the minus. And then if I just rearrange the equation, then I have QL over TL has to be less or equal to is that minus with a minus sign, right?
But they cancel out.
Minus TL over TH, right? No. H over TH. Okay. So let's be doing this. So if I multiply by minus 1, then I have QL is greater or equal to QH TH. Okay? And again, QL is negative. Right? And QH is positive. I'm sure you can do this a little bit better than me. I always get confused. Then you'll see that QH over TH plus QL over TL is less or equal to 0. Okay. So if it's reversible, then if it's irreversible, question, please? We're almost there. Okay? Right. As I promised earlier at the beginning of class, this class is not about calculating efficiency of engine. Right? We're interested in say, calculating for any reversible cycle. Right? Suppose I have a PV diagram. Over there, we only have a reversible engine operating under good temperature, right? But suppose I have something completely general like that, right? There's no temperature reservoir. There's more than 2 temperature reservoir. Completely arbitrary PV diagram, right? What can we say about it? Reversible cycle. Or for that matter, any reversible cycle. Okay. But I cannot define it, but suppose you can start at a starting point, initial starting point, right? You go around and you come back, right? What can we say about it? So let's first talk about the reversible. So what I can do is I can break down this this curve here, this closed curve, into a series of Carnot cycles, right? That's what I do. I can break it down into a series of Carnot cycles. solve. Okay? So, to go around this loop here, C, right? It's basically just adding Carnot cycle, right? Each of the Carnot cycle go in a clockwise manner. Okay, cycle A, and for each differential Carnot cycle, I have, let me use the differential, dq h I, this is the I cycle, right? For each Carnot cycle, the I Carnot cycle, right? Over thi plus dq low I, t low I. Is equal to 0, right? Okay.
Why is there bar over the left one, not the right one?
Say it again.
Is a bar over?
It's a bar. Oh, yes. Okay. So, if I sum over all the Carnot cycle, sum over all the Carnot cycle of dqhi over dhi plus dq rho I, right? Because individually it sums to 0, this has to be equal to 0 too. Okay? And let's see, and each of these Carnot cycle strip, what you have is Q, let's just concentrate on two of them, right? I and J, right? Q, L, J, well, I, and this is T, I, T, H, I, T, rho, I. Can you see this? Can you see all my indices? And then this is TH, J, LJ, okay? And then this is TQ, HJ, TQ, LJ, right? So, because this is a differential strip of a Carnot cycle, then you can approximate TH to be equal to TL, right? Okay? And also this cancels that approximately, right? So, or you don't even have to do that because it's already ensured for each cycle this is equal to 0, right? So what you have then, because you can say that the temperature is about the same, then this is just a sum over I of dqi, okay, over ti. And because this cancels, the heat that comes from one of these, the exit Carnot cycle I cancel the heat that comes from Carnot cycle J.
That's entering?
That's entering the next one.
They cancel out.
Because the heat supply,
yeah.
you supply the heat from this part of the Carnot cycle to that part of the Carnot cycle, right?
And because it's really differentially small, TH and TL are approximately the same?
Yeah, the fact that this is differentially small, you can assume that pH is equal to TL, right? And then this is what you get. And in the limit when this becomes differentially small, the limit when the strip becomes small, then you get what you get is I never liked this proof. It's not very satisfying, but it's the fastest proof. You know, I have another proof, but then I don't want to do it in class. In the discussion.
So the summation, that's not just an approximation, it's actually exact.
Say it again.
For the summation, for sigma 7.
Huh?
Yeah, so that, it's not just an approximation, it's exact.
In the limit, yeah, in the limit, then it's exact, right? And then you have what you have then is just a closed loop line integral of dq over t as the equal to 0.
What's the difference in qi and dqi and dqhi and dqli?
Ah. Let me do this again a little bit on Friday. I think there's a bit of confusion over this difference, right? How does it show up over here?
Yeah, how does the H and the L go away? I mean,
Yeah, and also, you know, like Matt's always not very happy with how to make sure you can account for all these gaps, right? This is not the greatest proof. But the final result holds, right? For a reversible cycle. This is always true. And you know what happened when this is true, right? You better get used to this. We talked a lot about this in ENN, right? Anytime I have a function like this, with a curve, right? Then this is an exact differential. State f is a state function. Right? And df is an exact differential. Right? For example, n. Right? So in this case here, you can see that that function here shows that this, right, is an exact differential. Okay. And then you can define a state function, and that's called entropy. The entropy is actually defined as so we're going to give like